Here we're examining another subset of R2. This time vectors of the form xy, but where x times y equals 1. We want to first find an example of two vectors in W2. So the requirement here is that x times y, the x component times the y component is equal to 1. So we could do something like 4 1/4, because the x component times the y component, x times y is equal to 4 over 4, which is 1. Okay, you guys know that. So that would work. 1 times 1 would also work, certainly, because the x component times the y component is equal to 1. Similarly, we could do -1, -1, because the x component times the y component is equal to 1. Okay, so we asked for 2. There's example of 3 examples of vectors in W2. A vector that is not in W2, anything where x times y does not equal 1. So something like 6 and 10. X times y there certainly does not equal 1. Just anything where when we take the product of the x component, the y component is not 1. Okay, so part B. If xy is in W2, would c times that vector always be in W2? So I'm thinking about the best way to, yeah, let's go with this. So if you suspect that something's not true, showing one example where this fails to be true is enough to knock the statement down. So let's just take an example. Let's take that 1, 1. So 1, 1. This is a vector in W2. So let's hold on, back up here. Let's let v equal this vector, and let's let our scalar c equal, let's say, 5. Then c times v in this case would be 5 times the vector 1, 1, which would be the vector 5, 5. And notice in this vector, the x component times the y component, this is x times y, equals 25, not 1. So here's an example of a vector v that's in W and a scalar c where c times v is not in W2. Okay. Part C. If u is equal to u1, u2, and v is equal to v1, v2, where those are both vectors in W2. So let's set this up. So if u is this vector u1, u2, and v is this vector v1, v2, where those are both vectors in W2. So that would mean that u1 times u2 is equal to 1, and v1 times v2 is equal to 1. And the question is, will u plus v be in W2? So u plus v would be, so we would just add the first components, so we'd have u1 plus v1 as the first component, and we would add the second components to get the second component of this sum here, so u2 plus v2. Now the question is, so is this in W2? Well, that would depend on whether the x component, u1 plus v1, times the y component, u2 plus v2, is equal to 1. If we multiply this out, notice that we'll have u1 times u2 when you multiply the first components, plus u1 times v2 when you multiply the outside components, plus, v1 times u2 when you multiply the inside components here. I'm doing the old FOIL method. Plus v1 times v2. Now notice, so u1, u2, this is equal to 1. v1, v2, this is equal to 1. So I suspect that, it's definitely not generally true that for any U1, U2, V1, V2, that this whole sum is going to come out to 1. I suspect often it will not equal 1. But this doesn't necessarily prove it at this point, because we can't say for sure, just based on what we've written here, that maybe you have a -1 here, maybe you have a 0 here, so maybe the sum is 1. That sort of thing could happen. We need to give a specific example of where this fails. So let's let the vector u be that 1, 1 vector. Well, and then what if v is also that 1, 1 vector? Let's say. So that way, these are both vectors in W2. If we take their sum, we get 1 plus 1, 1 plus 1. Notice that in this resulting vector, x times y, let me write it that way, x times y is equal to 2 times 2, which is 4, not 1. So in this case, 1, 1 plus 1, 1, the sum of these two vectors in W2 is not an element of W2. So this implies that W2 is not closed under addition. And in part B, we showed that it's not closed under scalar multiplication either. Okay, last question here. Is the 0 vector in W2? That's easy enough to check. I'm going to go up here and check that real quick. So the 0 vector is this vector in R2. Now x times y in this case is 0 times 0, which is 0, not 1. So the 0 vector is not contained in W2. So there's no way that this subset xy, where x times y is 1, there's no way that this is a vector space, because we've shown that it fails 3 of the requirements of a vector space. It's not closed under scalar multiplication. It's not closed under addition. When you take the sum of two vectors in this subset, you do not get a result that's necessarily in the subset, and it does not contain the 0 vector.